What is Lua? Lua is a powerful, efficient, lightweight, embeddable scripting language. It supports procedural programming, object-oriented programming, functional programming, data-driven programming, and data description. Lua combines simple procedural syntax with powerful data description constructs based on associative arrays and extensible semantics. Lua is dynamically typed, runs by interpreting bytecode with a register-based virtual machine, and has automatic memory management with incremental garbage collection, making it ideal for configuration, scripting, and rapid prototyping. This code snippet demonstrates how to output text in Lua. The print function is a built-in Lua function that outputs its arguments to the standard output. In this case, Hello Lua is passed as an argument to the print function, which will then display the text on the screen. This example is a simple demonstration of calling a function in Lua and passing a string argument to it. Setting up the Lua environment. Before diving into Lua programming, the first step is to set up the Lua environment on your computer. This involves downloading and installing Lua. You can install Lua directly from its official website or use a package manager if you're on Linux. Additionally, an integrated development environment, IDE, or a text editor that supports Lua can enhance your coding experience. The process doesn't involve actual Lua code. Setting up the environment is about preparing your computer to understand and run Lua scripts. Once Lua is installed, you can write Lua scripts using a simple text editor or an IDE. To run the scripts, you use the Lua interpreter by typing luafilename.lua in the terminal or command prompt, where filename.lua is the name of your script. This step is crucial, as it transforms your machine into a development environment where you can execute Lua code and build applications. Basic syntax. Lua's syntax is fundamental for writing any code in the language. It is simple and intuitive, making it easy for beginners to learn. Understanding the basic syntax is crucial for writing and interpreting Lua scripts efficiently. In the provided code snippet, we have examples of both single-line and multi-line comments in Lua. Lua uses double hyphens to denote a single-line comment, and long brackets and efficiently to denote a multi-line comment. Comments are ignored by the Lua interpreter and serve as notes or explanations for humans reading the code. The print function is used to display text. Here, it outputs "Hello World" to the console. This demonstrates a basic Lua script with comments and a simple output function. Comments. Comments are parts of the code that are ignored by the Lua interpreter. They are used to leave notes or explanations for the programmer or others reading the code, aiding in understanding the program's functionality or intent. Lua supports single-line and multi-line comments. In the provided code sample, sh is used to start a single-line comment. Everything following sh on the same line will not be executed by Lua. For multi-line comments, marks the beginning and marks the end. The enclosed text across multiple lines is ignored by the interpreter. These commenting techniques are valuable for documenting the purpose or logic of sections of code without affecting program execution. Variables and data types. In Lua, variables do not have types, only values do. A variable can hold values of any type without the need for explicit declarations. Lua has 8 basic types: nil, boolean, number, string, user data, function, and table. Let's delve deeper into assigning basic data types to variables. In the given code, 3 variables are assigned with different data types without explicit type declaration. Name is assigned a string value, denoting the title of this tutorial. Age is a number holding value 25, indicating perhaps the years of experience or age. Is learning Lua is a Boolean variable with the value true, indicating a positive affirmative state. The print function is then used to output the values of these variables. This demonstrates Lua's dynamically typed nature, allowing variables to hold any data type. Type coercion. Type coercion refers to the automatic or implicit conversion of values from one data type to another, e.g., strings to numbers, within an expression. In Lua, this mostly happens with arithmetic operations and string concatenation. Understanding how Lua handles these conversions is crucial for writing effective code and avoiding errors. In the first line, Lua coerces the string 10 to a number to perform addition, resulting in 11. In the second line, the number 1 is coerced into a string to concatenate with 10, yielding 101. However, in the third line, trying to add a number to a non-numeric string results in an error, demonstrating that Lua cannot always perform type coercion, especially when it doesn't make sense, such as adding numbers to non-numeric strings. If-then-else statement. The if-then-else structure in Lua allows programs to execute certain blocks of code only if specific conditions are met. It is a fundamental concept in programming for making decisions. An if block can stand alone or be followed by an else block, which runs only when the if condition fails. In this code, we check if the variable age is less than 18. If this condition is true, Lua executes the first block and prints minor. If the condition is false, meaning age is not less than 18, the program executes the code inside the else block, printing adult. This if-else statement allows the program to choose between two paths based on the condition's outcome. Loops, while, repeat until for. Loops let you run a block of code multiple times. Lua supports while, repeat until, and for loops, each serving different scenarios. While loops continue as long as a condition is true. Repeat until loops run until a condition becomes true. For loops iterate over a sequence of numbers or elements in a table. The while loop starts by checking the condition. If true, the loop's body executes and the condition is checked again, repeating this cycle. The repeat until loop always runs at least once and continues until the condition is true. The for loop initializes a variable, checks if it meets a condition, and adjusts the variable in each iteration until the condition is no longer satisfied. These structures help manage repetitive tasks, control flow, and iterate over data structures with ease. Nested control structures. Nested control structures occur when one control structure is placed inside another. This is common practice for handling complex conditions or iterative processes within scripts. It allows for more granular control of logic flow. In this code, two if statements are nested. The outer if checks if the age variable is greater than or equal to 18, identifying legal adults. Inside, another if differentiates between young adults, ages 18 to 29, and adults, 30 and above. This nesting allows the program to categorize ages into 3 groups instead of just adults and minors, enhancing decision-making capabilities. The else branches handle cases that do not meet the inner and outer conditions, respectively. Break and return. In Lua, break is used to exit a loop early, and return exits a function, optionally sending values back to the caller. Understanding how to use these can control the flow of your program. In the loop, numbers 1 through 4 are printed. When I equals 5, break exits the loop, so numbers 5 to 10 aren't printed. In getFirst, return gives back the first element of an array, exiting the function. Defining and calling functions. In Lua, functions are one of the core mechanisms to structure code. A function can be defined using the function keyword, followed by a name and a list of parameters in parentheses. Functions can return values using the return statement. Calling a function is done by writing its name, followed by parentheses, enclosing any arguments to pass to it. This code defines a function named greet that takes one parameter, name, and returns a greeting string concatenated with the name provided. The greet function is then called with the argument Lua, printing hello Lua to the output. This illustrates defining a function, passing it an argument, and using its return value. Parameters and return values. In Lua, functions can accept parameters and return values. Parameters allow you to pass data to a function, and return values allow a function to send data back to where it was called. This mechanism makes functions more flexible and reusable. In this example, a function named add is defined, which takes 2 parameters x and y. Inside the function, it calculates the sum of x and y and returns the result using the return keyword. When add 5, 3 is called, 5 and 3 are passed to the function as arguments, and the function returns 8. The result, 8, is then stored in the variable result and printed to the console. Multiple return values. In Lua, functions can return multiple values. This is a powerful feature that can simplify your code, allowing you to return more than one result from a function. You can capture these values in multiple variables or within a table. The function findMin and max takes 3 numbers as input and calculates the minimum and maximum using the math.min and math.max functions. It then returns both the minimum and maximum values. When calling find min and max, we capture these two return values into the variables minimum and maximum. This feature of returning multiple values from a function makes Lua versatile, as it can reduce the need for global variables or the use of tables for returning multiple values from functions. Variable number of arguments. In Lua, functions can accept a variable number of arguments without explicitly defining them in the function's signature. This is useful when the number of inputs a function might take is not known ahead of time. To accomplish this, we use art inside the function's parentheses. In the code provided, the sum function is defined to accept a variable number of arguments using inside the function represents a list of all arguments passed. We convert this list into an actual table using int, and then iterate over it with I-pairs to calculate the sum of all provided numbers. Finally, the total sum is returned. The print statement at the end demonstrates how this function can be called with any number of numeric arguments, showcasing its flexibility to handle a variable amount of inputs seamlessly. Named arguments, using tables. In Lua, functions typically receive arguments in a fixed order, which can be confusing or limiting with functions that have many parameters or optional parameters. To make this easier, Lua supports named arguments through tables. This technique involves passing a table to the function, where the table keys are the names of the parameters. This way, the order of the arguments does not matter, and you can easily work with optional parameters. In the given code, we define a greet function that takes a single argument, args, which is expected to be a table. Inside the function, we access the arguments by their names, args.name for the person's name and args.age for the person's age. We then concatenate these values into a greeting message. When calling the function, we pass a table that contains the named arguments. Name equals John, age equals 30. This makes it clear which argument is which, improving code readability and flexibility. This approach is particularly useful for functions with many parameters, or parameters that are optional. Closures and up values. In Lua, closures are functions that can access variables from its enclosing scope, known as up values. These up values retain their values between function calls, allowing the function to have state. This concept is powerful for tasks like encapsulating data, creating function factories, and more. Let's explore how a closure works with an example. In the given code, counter function is a closure with count as its up value. When counter is called, it initializes count to 0 and returns an anonymous function that increments count and returns its value. This anonymous function retains access to count even after counter has finished execution due to the closure. Each call to myCounter increments and prints count, demonstrating how the closure retains its state across calls. This pattern enables encapsulation and stateful programming in Lua. Tail calls. In Lua, tail calls are function calls performed as the final action in a function. When a function calls another as its last operation, the calling function can be removed from the stack before starting the called function, optimizing recursion and saving stack space. This feature is particularly useful for recursive functions with large or indefinite recursion depths. In this example, tail recursive sum calculates the sum of numbers from 1 to n using tail recursion. The function is tail recursive because the final action it performs is a call to itself, tail recursive sum. The accumulator parameter is used to accumulate the sum. Each recursive call adjusts the current number n and the accumulator until n reaches 0, where it returns the accumulated sum. This pattern allows Lua's interpreter to optimize the recursive calls, avoiding the build-up of call stack frames. Introduction to tables. In Lua, tables are the main and only data structuring mechanism capable of representing arrays, dictionaries, and more. They are powerful and flexible, allowing indices to be numbers, strings, or any other value except nil. Let's start with a basic example to create a table and add some data to it. Here, fruit basket is our table. We start by adding two items, apple and banana, at positions 1 and 2 respectively. This resembles an array. However, tables in Lua can also have named keys, as shown with favorite mapping to grapes. To access elements, you then use either the numeric index for the array part or the key name for the named part. This example demonstrates how Lua tables are used to create a mix of array-like and dictionary-like structures, creating and indexing tables. In Lua, tables are the main, in fact, the only data structuring mechanism. They are powerful, serving as arrays, dictionaries, and even objects from OOP perspective. Creating a table is simple and direct. Indexing, or accessing the elements of a table, can be done using either dot notation or square brackets. This code snippet first creates a table named myTable with 3 elements. These elements are strings representing different fruits. Tables in Lua are 1-indexed, meaning the indices start at 1. Thus, myTable1 refers to the first element, apple. The second part demonstrates adding a new key-value pair to the table, where city is the key and New York is the value. This is done using dot notation. myTable.city is then used to access and print the value associated with the key city. Both dynamic indexing, using numbers, and named keys, like city, showcase the versatility of Lua tables. Tables as arrays. In Lua, tables can be used as arrays, which are essentially ordered collections of items. Unlike some other languages, Lua arrays are 1-indexed, meaning the first element is at index 1 instead of 0. This can be a bit tricky for those coming from 0-indexed languages. Let's go through a basic example to create an array, add elements to it, and access them. Here, we first declare an array named fruits with 3 elements. When we print fruits1, Lua returns apple, as arrays are 1-indexed. Then we add another element, date, at the 4th position in the array. When we print fruits4, it correctly displays date. This example illustrates how to create, add elements to, and access elements within a Lua table used as an array. Note, we skipped index 3 deliberately to showcase that Lua tables used as arrays do not have to be sequential or contiguous. Missing indices are simply nil. Tables as dictionaries. In Lua, tables can also be used as dictionaries or hash maps in other programming languages, where each value is associated with a unique key. This concept enables storing non-sequential and heterogeneous data in a structured way, facilitating the creation of complex data structures. In this code snippet, a person table is created with 3 key-value pairs, name, age, and is employed. Keys are strings that identify each element in the table. To access a value, you can use either the dot notation, person.age, when the key is a valid identifier, or the square bracket notation, person name, for keys that are not valid identifiers, or when accessing keys stored in variables. This flexibility allows the table to act as a versatile dictionary for holding various types of data. Iterating over tables. In Lua, tables are used to organize data into key-value pairs. One common operation is iterating over these pairs to perform operations on each element. Lua provides several methods for iteration, with pairs and iPairs being the most notable. Pairs is used for iterating over all elements in a table, regardless of key type, while iPairs is specifically for iterating over sequential integer keys. Let's focus on using pairs to iterate over a table. In the provided code snippet, a table named fruits is declared with 3 key-value pairs, where the key is the fruit's name and the value is some quantity. The for loop utilizes the pairs function to iterate over each element in the table. During each iteration, key and value variables are assigned to the current element's key and value respectively. The print key value statement inside the loop prints each fruit's name and its quantity. This process repeats for every key value pair in the table, thereby demonstrating how to iterate over tables in Lua using pairs. Table operations: insert, remove, sort. Lua tables are dynamic arrays that can perform various operations such as insertion, deletion, and sorting. These operations help manage table data efficiently. Let's explore how to insert elements into a table, remove elements from a table, and sort a table using built-in Lua functions. This example demonstrates 3 key table operations in Lua. Initially, we create a table fruits containing some elements. Using table.insert fruits date, we add a new element date to the end of the table. The table.remove fruits1 statement removes the first element from the table and returns it. After modification, we sort the table alphabetically with table.sort fruits. Finally, we iterate over the fruits table using iPairs and print each element. This sequence of operations showcases how to manipulate table data using insert, remove, and sort functions. Multi-dimensional tables. In Lua, multi-dimensional tables are essentially tables within tables. They enable you to create complex data structures, such as matrices. Understanding how to work with these can significantly enhance your Lua programming abilities. In the provided example, we declare a variable named matrix, which represents a 3x3 matrix. Each element of the top-level table, matrix, is itself a table representing a row in the matrix. To access an element, we use two indices, the first for the row and the second for the column. As shown, accessing matrix 2, 3 retrieves the element in the second row and the third column, which is the number 6. This demonstrates how multi-dimensional tables can be utilized to represent and operate on complex data structures in Lua. Using modules. In Lua, modules are a way to organize and reuse code across multiple files. They allow you to define functions, variables, or tables in one file and make them available to other files. Below, we demonstrate how to create a basic module and use it in a main program. In myModule.lua, we create a table M, which acts as the module. We define a function greet within this module. At the end of myModule.lua, return M makes the table, and hence the functions it contains, available to other files. In main.lua, we use require myModule to include and assign the module to myModule. This allows us to call myModule.greet, passing a string argument to print a greeting. This demonstrates the fundamental pattern of defining and utilizing modules in Lua. Creating modules. In Lua, modules are a way to package related functions, variables, and statements in a separate file, making them reusable and maintainable. Creating modules involves two steps: writing the module file and then requiring it in another script. In myModule.lua, we declare a local table M to hold the module's functions. We define a function sayHello within M and return M at the end of the file. This makes M act as the module itself. In script.lua, we load our module with require myModule, which runs the file and returns the table M, allowing us to call myModule.sayHello. The module's functionality can now be easily reused. Lua file structure. In Lua, a script or module typically begins with a declaration of variables and module-specific settings. This setup is crucial for organizing code, controlling scope, and facilitating code reuse. Below is a simple example structure of a Lua file demonstrating these concepts. This Lua file starts with a local variable M, which acts as a table to hold all the functions we want to export from this module. The sayHello function is defined within this table, making it a part of the module's public interface. At the end of the file, M is returned, making sayHello accessible to any script that requires this module. This structure helps in encapsulating functionality and avoiding global namespace pollution. Package.path and package.cpath. In Lua, package.path and package.cpath are used to control how Lua locates modules when they are required. Package.path is used for Lua modules, and package.cpath is for compiled C modules. These variables contain paths that Lua searches in order when you use the require function to include a module. The code prints the current settings of package.path and package.cpath. These paths are a series of directories separated by semicolons on Windows or colons on Unix-based systems. Each path can contain a question mark, which Lua replaces with the name of the module being searched. This system allows Lua to locate and load modules whether they are written in Lua or compiled as C libraries. Require function. In Lua, the require function is vital for working with modules and packages. It allows you to include and use the functionality provided by other Lua files within your current script, promoting code reuse and modularity. The function ensures that a module is loaded only once, regardless of how many times it is requested. In this example, require is used to load a module named myModule. The module is expected to return a table, or library, that contains functions or variables. Using local myModule, we catch the return table from myModule.lua, allowing us to access its functionalities, like myFunction. The key point here is that require not only executes the target file, but also effectively returns its content, represented usually by a table. This makes the functions or variables defined in myModule available through the myModule prefix in the main script. Distributing and using Lua Rocks. Lua Rocks is a package manager for Lua modules, allowing users to install, update, and manage Lua software easily. It's akin to pip for Python or npm for Node.js. Distributing your Lua module via Lua Rocks makes it accessible to a wider audience. Here, we'll explore the basics of creating a RockSpec file for distribution and installing a package using Lua Rocks. To install a package with Lua Rocks, use Lua Rocks install package name. For distributing, a RockSpec file describes your package. It includes the name, version, source URL, e.g., a GitHub repository, a description, summary, detailed, homepage, and license, and build details, usually specifying the Lua files that constitute the module. The example RockSpec shows how to structure this file for a hypothetical package named myPackage. After creating a RockSpec, you can distribute your module through Lua Rocks, making it easily installable by others. Metatables and meta methods. In Lua, metatables allow us to change the behavior of tables. For example, we can define how operators like addition or subtraction work with tables, how tables behave when accessed with non-existent keys, and more. Meta methods are the functions stored in metatables that define these behaviors. Let's look at an example where we create a vector class and use metatables to enable vector addition. This code defines a basic vector class that allows vector addition. By using setMetatable obj self, we set the metatable of each vector instance to the vector table itself, allowing us to use the index meta method to access vector methods. The addMeta method lets us define how two vector instances can be added together, returning a new vector instance with the sum of their coordinates. When vec1 plus vc2 is performed, Lua looks up the addMeta method in the metatables and calls it, resulting in vec3 being a new vector with summed coordinates. Using OOP in Lua. Lua does not have built-in support for object-oriented programming, OOP, but it can be implemented using tables and metatables. OOP principles such as encapsulation, inheritance, and polymorphism can be demonstrated through the clever use of these features. Here's how to create a simple class in Lua. This code snippet demonstrates creating a simple account class in Lua. The account table serves as a class from which objects can be instantiated. The create function initializes new objects with a balance and uses setMetatable to associate the object with the account class, metatable. The notation allows us to define methods that automatically receive the object instance, self, as the first argument, enabling operations like deposit and withdrawal. This technique illustrates how Lua can simulate classes and object-oriented behavior using tables and metatables. Creating classes. In Lua, classes are not provided as a built-in concept, but can be emulated using tables and metatables. This allows objects to have properties and methods. Let's create a simple person class as an example. The person table serves as a class from which objects can be instantiated. The index property is used to link an object's metatable to the person class, allowing the object to access the class's methods. The person.new function is a constructor that creates and returns new instances of the class. It uses setMetatable to assign the newly created table, self, a metatable that links back to person. Finally, personSpeak is an instance method, defined using the colon syntax, allowing access to the instantiated object's properties, self.name, inside the method. Inheritance. Inheritance in Lua allows one class, called a subclass or derived class, to inherit the properties and methods of another class, known as a superclass or base class. This mechanism is the cornerstone of object-oriented programming, enabling code reusability and the extension of existing code. Lua does not have built-in object-oriented constructs, but we can use tables and metatables to simulate this behavior. The code begins with defining a base class animal. Using animalNew, we initialize a new animal object. This method sets the object's metatable to the animal table and assigns the name property. The animalSpeak method is a simple function that outputs the animal's name. Inheritance is implemented by creating a dog class that calls animalNew to inherit animals' properties and methods. We override the animal base class's speak method in dog to customize the behavior for the dog instance. Finally, we create an instance of dog named Rex and call its speak method to observe the overridden behavior. Privacy with local tables. In Lua, achieving privacy in object-oriented programming involves using local tables. This concept allows us to encapsulate data and ensure that only specific parts of our program can access and modify it. By utilizing local tables, we can simulate private attributes and methods that are not directly accessible from outside the object. The code defines a new account function that simulates a bank account. Inside new account, a local table self acts as the object holding the account's balance. Private functions withdraw and deposit modify self.balance directly, but are not exposed outside the object. External access to self.balance is controlled through a public interface returned at the end of new account. This interface exposes three methods: withdraw, deposit, and get balance, the latter providing read-only access to the balance. The account's actual balance is not directly accessible from outside, ensuring encapsulation and privacy. This pattern shows how local variables and closures can create private attributes and methods in Lua. Strings and string manipulation. In Lua, strings are immutable sequences of characters used to represent text. You can create strings by enclosing the text in single quotes or double quotes. This code snippet demonstrates how to declare a string in Lua. The variable greeting is assigned a string value, hello world. The string is enclosed in single quotes, but double quotes could have been used as well. Since strings are immutable in Lua, the value of greeting cannot be changed directly once it is set. Patterns and matching. Lua offers powerful pattern matching capabilities, which can be utilized for searching, replacing, and capturing specific parts of strings. The pattern matching system in Lua is not as complex as regular expressions found in other languages, but is sufficiently capable for many tasks. Patterns in Lua are strings, which define the rules to match or capture sequences in other strings. In this code, we use Lua's string.match function to check if the string email matches the pattern defined. The pattern sentW+sent at abd plus sentW+ is looking for an email-like structure where sentW+ matches one or more alphanumeric characters and sent matches a literal dot. If the email string adheres to this pattern, valid email is printed. Otherwise, invalid email is shown. This demonstrates a simple use of pattern matching for basic data validation. Captures. In Lua, string patterns can include special capture mechanisms that extract substrings matching parts of the pattern. This feature is useful for parsing and transforming string data efficiently. Let's see how it works with a practical example. The code uses the string.gmatch function to iterate over all occurrences of the pattern sentD+, which matches one or more digits in the text string. Each match found by gmatch is captured and then printed. sentD+ serves as the capture pattern here, allowing us to extract and utilize each number, i.e. 2 and 5, from the text. Captures are crucial for dissecting strings based on complex patterns, supporting both utility and data processing tasks in Lua. gsub and find functions. In Lua, string manipulation plays a crucial role in handling text data. Two powerful functions for this purpose are gsub and find. The gsub function is used for replacing occurrences of a pattern in a string with another string, whereas find locates the start and end positions of a pattern within a string. In the provided code, string.gsub is used to replace world with Lua in the string hello world. It returns the modified string and the number of replacements made. The output is hello Lua and 1, indicating one replacement. Then, string.find is utilized to locate the substring world in hello world. It returns the start and end positions of the substring within the main string. The output shows the positions as 8 and 12, indicating world starts at position 8 and ends at position 12. Reading from and writing to files. File handling in Lua allows you to read data from files and to write data to files. This is typically done using io.open, file read, file, and file close. The io.open function is used to open a file, which returns a file handle. This handle is then used for subsequent operations on the file. Let's go through both reading from and writing to a file in Lua. The code snippet first opens a file named example.txt in read mode, R, and reads its entire content using file read to A, which reads the whole file. After reading, it closes the file using file close. Then, it opens, or creates if it doesn't exist, another file named output.txt in write mode W, and writes the previously read content into it using file write content. Finally, it closes the file. This example demonstrates basic file reading and writing operations in Lua. Working with binary files. In Lua, working with binary files is crucial for applications that need to read or write data in a non-text format. This requires understanding the io.open function for file operations and the various modes for opening a file. In binary mode, files are opened with a B in the mode string. Let's delve into reading and writing a binary file. The code example demonstrates how to open, write to, and read from a binary file in Lua. Initially, a binary file named example.bin is opened in write WB mode. With file write string.char 0x000100x0xab, we write binary data directly to the file, representing bytes with hexadecimal values. Following this, the file is closed and then reopened in read RB mode. With file read SHA, we read the entire content of the file as a binary string. Finally, the content is printed out, and the file is closed once again. This process illustrates the basic flow of working with binary data in Lua. File modes and buffering. In Lua, file modes determine how a file is opened for various operations, such as reading, writing, or appending. Buffering affects how data is temporarily stored before being written to or read from a file. Understanding these concepts is crucial for efficient file manipulation. This code snippet demonstrates opening a file in write mode, W, which allows you to write to the file, potentially overwriting existing content. The write method is used to put text into the file. After writing, flush is called to ensure all buffered data is written to the file system, a crucial step for ensuring data integrity, especially when working with buffered I/O. Closing the file with close finalizes the operation and releases any system resources associated with the file. This example showcases how to employ file modes and understand the importance of buffering and explicitly managing it. Seeking within files. In Lua, seeking within files allows you to change the current position of the file pointer. This is crucial when you need to read, write, or otherwise manipulate data at specific points in a file without having to process its entirety. The seek method of a file object is used to achieve this. The method takes two arguments. The first specifies the base position, set, cur, or end, and the second specifies the offset from that position. If called without arguments, it simply returns the current position in the file. In this code snippet, we open a file named example.txt in read mode. The first seek call without arguments returns the current position of the file pointer, which is typically at the beginning of the file, position 0, unless previously moved. Next, we use file seek set 10 to move the file pointer to the 10th byte from the beginning of the file. The third seek call, again without parameters, returns the new position of the file pointer, confirming the successful movement. Finally, we close the file to free up resources. This process demonstrates how to navigate within a file, enabling fine-grained control over file interactions. Error handling with pcall and xpcall. In Lua, pcall, protected call, is a function that calls another function in protected mode. This means if the called function throws an error, pcall catches it and returns a status code indicating whether the call was successful, thus preventing the error from propagating. The code defines a function miteRr that, when called, immediately throws an error. Using pcall, we attempt to call miteRr. Pcall returns a Boolean status and an error message error. If miteRr throws an error, status becomes false, and error contains the error message, allowing us to handle the error safely. If miteRr did not error, status would be true, and error would contain any return value from miteRr. Debugging tools and techniques. In Lua, debugging can be approached through several tools and techniques to isolate and fix errors. Even without sophisticated IDEs, Lua provides built-in functions and conventions to effectively debug code. Here we'll explore basic but powerful strategies like using print statements, leveraging the debug library, and employing assertions. In this code, assert checks if both parameters are numbers and triggers an error when the condition isn't met. This is a simple but effective way to ensure your functions receive correct data types, helping prevent logical errors. The debug library isn't explicitly used here, but the assertion function acts as a rudimentary debugging tool. By explicitly stating the expectations of the inputs, it makes tracking down type-related issues simpler. Although this code results in an error, it's a demonstration of proactive error handling and ensuring data integrity through assertions. Using assert and error. In Lua, error handling is a crucial part of robust programming. Two fundamental functions used for this purpose are assert and error. The assert function is used to throw an error if a given condition is not met. The error function is used to terminate the program and optionally return an error message. In the provided code, we define a function safe_divide that accepts two parameters a and b. The assert function is used to ensure that b is not 0. If b is 0, assert throws an error with the message cannot divide by 0. We then use pcall to call safe_divide safely, passing 4 and 0 as arguments. If an error occurs, pcall returns false and the error message, preventing the program from crashing. Stack traces and error level. When an error occurs in Lua, the interpreter can generate a stack trace that shows the function call sequence that led to the error. This can be very helpful for debugging. Lua provides the error function to generate an error and the debug.traceback function to get a stack trace. The error level influences the starting point of the trace. In this code, second function generates an error via the error function. Since second function was called by first function, the stack trace will show this sequence. The default behavior includes the line that caused the error and its call sequence. This trace helps identify where the error occurred and through which functions the program flowed to get there. Understanding and utilizing stack traces and error levels are crucial for diagnosing and fixing bugs in code efficiently. Introduction to Coroutines. In Lua, coroutines are powerful tools for managing how functions execute. Unlike a regular function that runs from start to finish without interruption, a coroutine can pause its execution, yield, and then resume from the point it left off. This makes coroutines particularly useful for tasks that require cooperative multitasking or the simulation of multiple threads within a single-threaded environment. This example demonstrates the basics of using coroutines in Lua. The generator function creates a coroutine that yields numbers from 1 to x. The coroutine.wrap function is used to turn a function into a coroutine and automatically handles its execution. When called, generator5 returns a coroutine that yields values from 1 to 5. The for loop iterates over these values, effectively demonstrating how the coroutine pauses at each yield and resumes on the next iteration of the loop. This ability to pause and resume execution makes coroutines a versatile tool for a wide range of programming tasks. Creating and managing coroutines. In Lua, coroutines are powerful tools that allow you to pause and resume functions at specific points, enabling cooperative multitasking. A coroutine can be in one of several states: running, suspended, dead, or normal. Creating and managing these coroutines is straightforward with the coroutine library. In this example, we create a generator function that yields numbers from 1 to x. The coroutine.create function is then used to create a coroutine with this generator function. Next, we enter a loop where we repeatedly resume the coroutine using coroutine.resume, which restarts the coroutine's execution until it yields again. The coroutine yields at each iteration inside the generator function, thanks to coroutine.yieldI, allowing us to print each yielded value. This process continues until the coroutine is dead, when success is not true, which happens after yielding all numbers up to x. This illustrates how to create, start, pause, and resume a coroutine, managing its execution flow cooperatively. Yield and resume. In Lua, coroutines are cooperative threads. They allow multiple parts of a program to run independently. The yield function suspends a coroutine's execution, letting other coroutines run. Resume restarts a coroutine from where it left off. Let's explore how these work together. This example creates a coroutine that yields successive numbers starting from 1. The producer function creates and returns a coroutine. Inside this coroutine, an infinite loop increments a number and yields it each time the coroutine is resumed. The code demonstrates resuming the coroutine 3 times, each resulting in the printout of the next sequential number. The coroutine.resume.co statement resumes the coroutine CO, which continues from its last yield point, returning true, indicating successful resume and the yielded value. Coroutine communication. Communication between coroutines in Lua is facilitated through the yield and resume functions, allowing data to be passed back and forth between a coroutine and its caller. In this code, producer function creates a coroutine that yields numbers from 1 to 5. Each coroutine yield I pauses the coroutine, sending I back to the consumer. The consumer function starts and continues the coroutine with coroutine.resumeProd, receiving each yielded value. With each resume, the coroutine resumes where it left off. This loop in consumer demonstrates basic communication, showing how coroutines can interchange data, facilitating a producer-consumer pattern. Use cases for coroutines. Coroutines in Lua are powerful for creating cooperative multitasking within a single-threaded environment. This allows multiple tasks to run seemingly in parallel by yielding and resuming execution at specific points. Understanding use cases for coroutines can help apply them effectively in real-world scenarios. This example illustrates how coroutines can be used for non-blocking I/O operations. Here, we define a generator function search that searches for a pattern in input lines without blocking the main program execution. The search line function reads lines and checks for the pattern, yielding control when necessary. Employing coroutine.wrap, the search function is transformed into a coroutine, allowing the main program to continue its execution without waiting for all lines to be processed. This non-blocking behavior is particularly useful in scenarios requiring responsive user interfaces or when performing long-running tasks in background. Understanding Lua garbage collection. Lua uses a garbage collector to automate memory management, a process which helps to reclaim memory occupied by objects that are no longer in use by the program. This system reduces the potential for memory leaks and the need for manual memory management by the programmer. Understanding how the garbage collector works can help in optimizing the performance of Lua programs. In the provided code, the collect garbage function is used first with the argument collect to force a garbage collection cycle. This operation compels Lua's garbage collector to run and clean up memory that is no longer referenced by the program. After that, collect garbage is called again with the argument count, which returns the total memory in kilobytes currently used by Lua. This can be useful for monitoring the memory usage of a Lua program and understanding the impact of garbage collection cycles on performance and memory consumption. Weak tables. In Lua, tables can have a powerful feature called weak references through weak tables. These are especially useful in memory management, where they allow tables to reference objects without preventing those objects from being collected by garbage collection. This feature is crucial for creating caches or mappings that should not interfere with the garbage collector's job. In this code snippet, a table A is created, and its metatable is set to another table B with the score mode field set to K, making A a weak table with weak keys. A key value pair is added to A with a new table as the key. After setting the key variable to nil and manually invoking garbage collection by collect garbage, the key, and consequently the value associated with it, is collected, leading to an empty table A. If we were to iterate over A, nothing would be printed, since the key has been collected due to its weak reference. Optimizing memory usage. Optimizing memory usage in Lua involves understanding how garbage collection works and utilizing various strategies to minimize memory footprint. It's crucial in environments with limited resources. Here, we'll look into a simple technique involving the reuse of tables to conserve memory. The example demonstrates table reuse to minimize memory allocation. The first loop initializes a table T with 1,000 subtables, each containing a unique value. Instead of creating new tables in subsequent operations, the second loop reuses T, updating each subtable's value. This practice conserves memory by avoiding the creation of additional tables, which is impactful in scenarios where table allocations/deallocations are frequent and could lead to excessive memory use or increased garbage collection overhead. By reusing tables when possible, we better manage Lua's memory usage and improve application performance. Garbage collector control. In Lua, memory used by objects that are no longer accessible is automatically reclaimed by a garbage collector, GC. However, programmers can interact with the garbage collection process to optimize performance. This can be achieved by modifying the garbage collector's behavior through specific functions provided by Lua. The code demonstrates basic control over Lua's garbage collector. First, it forces a garbage collection cycle with collect garbage, collect, ensuring that all possible memory has been freed before measuring. It measures initial memory usage in kilobytes with collect garbage count. Then, it stops the garbage collector with collect garbage stop to prevent it from running during performance-critical operations. After these operations, the garbage collector is restarted with collect garbage restart. Finally, it measures the memory usage again. By comparing count before and count after, one can analyze the impact of the performed operations on memory usage. Lua C API. The Lua C API allows C code to interact with Lua, enabling Lua scripts to call C functions and C code to manipulate the Lua stack. This bridges C and Lua, making it possible to extend Lua with C for performance or to provide bindings to C libraries. The code demonstrates defining a C function that can be called from Lua. The function LMyFunction takes one integer argument from Lua, multiplies it by 10, and returns the result back to Lua. Lua checkInteger is used to get the argument from the stack, ensuring type safety. The result is pushed to the stack using Lua pushNumber, and it returns 1, indicating the number of values it pushes back to Lua. Embedding Lua in C programs. Embedding Lua in C programs allows developers to leverage the scripting capabilities of Lua within a C application. This is particularly useful for applications needing a flexible and user-configurable scripting interface. The following example demonstrates how to create a Lua state, run a simple Lua script from a string, and then close the Lua state. Understanding how to interact with Lua from C opens up many possibilities for extending C programs. The code starts by including the necessary Lua headers. Lua new state creates a new Lua state, a necessary step for executing any Lua code. Lua openlibs opens the standard Lua libraries, which enables the use of built-in functions like print. Lua doString executes the Lua code given as a string, which in this case simply prints a message. If an error occurs during script execution, it gets printed to the standard output. Finally, Lua close cleans up and closes the Lua state. This pattern forms the basis of embedding Lua scripts into C applications, providing a powerful tool for scriptable interfaces and functionalities. Using Lua with C++. Integrating Lua with C++ allows for the flexibility of Lua scripting combined with the power and performance of C++. This approach is widely used in game development and applications requiring scripting capabilities. Here, we'll look at a basic example of how to call a Lua function from C++. The code snippet demonstrates the basic steps to integrate Lua with C++. First, it includes the Lua header and creates a new Lua state. The Lua openlibs line opens the standard Lua libraries, which is necessary for most operations. Lua dofile example.lua executes a Lua script file named example.lua. If the execution is successful, it proceeds to call a Lua function named Lua function within that script by using Lua getGlobal Lua function. It checks if the global name is indeed a function, and if true, it calls the function with Lua pcall L000, which effectively has no arguments and no expected return values. Finally, the Lua state is closed with Lua close L. This is a streamlined way to extend C++ applications with Lua scripts. FFI, Foreign Function Interface. FFI allows Lua to call C functions directly from its codebase. This feature is essential for performance-critical applications or when needing to use existing libraries written in C. We'll explore how to use FFI to call a simple C function that adds 2 integers. Firstly, we require the FFI module to use FFI functionalities. The fi.cdef function is used to declare the C functions we want to call, specifying their signatures, in this case, an add function that takes 2 integers and returns an integer. FFI.load is used to load the shared library mylib here, containing the defined C function. Once loaded, we can call lib.add directly from Lua, passing the necessary parameters and printing the result. Metaprogramming. Metaprogramming in Lua involves techniques that allow programs to treat other programs as their data. It means that a program can be designed to read, generate, analyze, or transform other programs, and even modify itself while running. A key concept in Lua metaprogramming is the meta table, which allows us to change the behavior of tables. In this code snippet, we first create an empty table named myTable. We then set a meta table for myTable with an storeIndex meta method. The storeIndex meta method is a fallback function that gets called when we try to access a key in the table that doesn't exist. In our case, if some key does not exist in myTable, instead of getting a nil value, the storeIndex meta method is invoked, returning the string key does not exist. This demonstrates how metatables can be used to customize table behavior in Lua. Performing Lua bytecode manipulation. Lua bytecode manipulation allows for low-level modifications of Lua scripts, enhancing performance, obfuscating code, or implementing features not directly available in Lua. It involves compiling Lua into bytecode, modifying this bytecode, and then executing it. Due to its complexity and potential risks, including stability and security concerns, it's essential to proceed with caution. This code demonstrates a basic framework for Lua bytecode manipulation. The string.dump function is used to obtain the bytecode of a given Lua function. The manipulation, which is placeholder text in this example, as actual manipulation depends on specific goals, would occur on the bytecode variable. After manipulation, load is used to convert the modified bytecode back into a Lua function that can be executed. To illustrate, an original func is defined, manipulated, theoretically, in this snippet, and then executed via manipulated func, showing how bytecode manipulation can alter the behavior of the original Lua code. Security considerations when using Lua. Security in Lua scripting involves ensuring that Lua code cannot harm the host application or system. While Lua itself is secure, the functions it exposes from the host application can introduce risks. It is crucial to sandbox Lua environments, especially when running untrusted code. The provided code demonstrates a basic approach to sandboxing in Lua. It loads untrusted code in a controlled environment by setting a new, empty environment table, NV, with setFenv. This prevents the untrusted code from accessing or modifying the global environment or external libraries, effectively sandboxing it. The function safe_load returns the environment table after the untrusted code has been executed, allowing for inspection of what was defined. However, it's important to note that load and setFenv functions have nuances in different Lua versions, and additional security measures may be necessary for a robust sandboxing solution.